Hey there, let's talk a little bit about conical pendulums. So you're probably familiar with pendulums, and those are just a bob hanging on a string that you swing back and forth. Um, but a conical pendulum is going to be moving in a circular motion. So instead of moving linear back and forth, what we have is the bob moves at a constant velocity in a circular motion, like so. And what we want to do is we want to analyze the forces involved with this. And they're dependent upon the angle and the tension and the length of this and all these different parameters. So I'll walk through an example, and then you can answer a couple questions about another one. It's a pretty common problem with circular motion. But the basic idea is that, we got to have some net force that's acting toward the center of the circle. And that comes from from the tension that's being produced by the string that's attached to the bob. And what we'll do is we'll break that into components, and you'll see that there's a component that always points inward towards the center. Don't pay attention to these cosine and sine, because that depends on the angle that we're talking about. So if you look online at some tutorials, it's just like projectile motion. They're going to give you equations that say that, this is always the sine, the tension times the sine theta, like so. It depends on the angle that you're being used. So I suggest you just use the angle they have, draw your force diagram, and work from there. So anyway, you can play with this if you want. You just Google GeoGebra conical pendulum, open it up, and you can play around with it, because you can mess with like the radius and see how that affects it, or change the angle. That's just the angle we're looking at. Anyway, not much to it, but so let's look at an example. So let's say we had a conical pendulum going. So this is moving at constant velocity in a circle. The bob, that's this, whatever's attached to the end of the string, has a mass of 3 kilograms. And it's connected to some spring scale, and we know that the tension force is 12 newtons. And the angle from the horizontal, so the way that we defined it in this problem, is going to be 25 degrees here. Sometimes you'll see that it's measured here from the vertical, or it might be measured here. So again, you just work with whatever you have, and the trig will take care of it. And we know the length of the string that's attached to it is 0.46 meters. So those are all our knowns. And what we're asked is, what's the linear velocity, or the tangential velocity of the bob as it's going around, and what's the period? How long will it take to make one complete revolution? So let's start. So let's say we just wanted to use kinematics. We could say, well, I know that the velocity is going to be 2 pi r divided by t. Well, I can't do that because, first off, I don't know the radius. The radius would be this part right here. My picture is kind of messed up, but we don't know the radius and we don't know the period, so I can't find the velocity straight from kinematics. Maybe acceleration. So centripetal acceleration, which is v squared. I don't know v, so I'm not going to be able to do that, but just go ahead and write it. So it looks like I'm going to need to maybe use dynamics, or maybe what if I found the radius? So let's try to find the radius. This picture is off. The circle should actually be like so, because where the string's connected at is actually in the center of the circle. And so what we can see is that the string and the radius form a right triangle. So I'm going to pull that out and see if I can determine r. So let's determine the radius. Now, this is just for this problem. Don't try to fall into the trap of thinking every problem is going to be the same. It depends on what they give you, depends on what they ask for, and we just work with what we know. I'm going to find the radius just to see if I'll be able to use it somewhere. I don't think so, because I don't have t and I don't have v, but I may need it at some point. So let's go ahead. I'm going to draw this triangle right here. So what I have is I have my tension force. Notice I didn't use t for tension. I used ft. That's so that I don't get confused with the period, which is big T. And then I have r, which is right here. And then I have, some other force or some other side, I don't really care about that. All I care about is completing my right triangle, because I know that the length of this is 0.46 meters. Okay, so I know this angle is 25. And then I know that there's a right angle right here. So I know that this missing angle here is going to be 65. I know that's really small, but all I did was subtract 90 minus 25 to get the 65. So now I have a right triangle. And I'm trying to find the radius, and I know the hypotenuse. So what I have is that the sine of 65 is going to be r over 0.46. So the radius is going to be 0.46 sine 65. So the radius, when I calculate that, is going to be 0.416902 meters. So just under half a meter is the radius. But again, when I plug that in, I still don't know that. I don't know the period, and over here I don't know the velocity. So anyway, we're going to have to get into dynamics. So let's start with a force diagram, see what that looks like. So based on this, there's my object, and I have some tension going up in this direction. And of course I have some weight. So those are the two forces. I'm going to define my coordinate system to be like so. So I have x in this direction and y in this direction. So all I need are the components of this this tension force, and that would be this direction, my force and tension in the x, and then I have a force of tension in the y direction, which would offset the weight. So I'll go ahead and draw these in. Oh, I know this is 25 degrees. So what I'm going to do is I'm going to draw them over here where I have my angle. So this would be the force of tension in the y direction and the force of tension in the x direction. And this force here is what's producing my centripetal acceleration. This one is offset with this one. So the force of the tension in the y is going to be the same in magnitude as the weight. I know that the vectors aren't the same length, but this is an equilibrium. The pendulum is not moving up and down. It's just moving in the x direction. It's going around and around in the x. So I could just make a note of that. We could say that the sum of the forces in the y direction is equal to the mass times the acceleration in the y, but the acceleration in the y is 0. So the sum of the forces in the y is equal to 0. And I don't think there's any need to go on with that. We know that this is going to be the opposite of the weight. So now let's go over to x and see what's going on. So the sum of the forces in the x direction is equal to the mass times the acceleration in the x. But the acceleration in the x for circular motion has a special name. It's centripetal acceleration. So the sum of the forces in the x, the only force in the x is going to be the force of the tension in the x direction, which is equal to the mass times the centripetal acceleration. But I'm going to go ahead and substitute this value, this equation in there. So I get v squared over r. Okay, so I know the mass, I know the radius, I don't know the velocity, and right now I don't know the force of t in the x. But we can figure that out using a little bit of trig. So my force of tension was 12 newtons. So my force of tension in the x is going to be the force of tension. And since it's next to the angle, cosine 25. And calculating that, you get 10.8757 newtons. So we'll use this in just a second. I'm going to rearrange this. I'm trying to solve for V, because once I got velocity, then I can go back and we can determine the period. So I'm going to divide by M and multiply by R. So I get the force of tension in the X direction times R divided by M is equal to V squared. Let's get rid of the square. We take the square root. So the velocity is going to be the square root of the radius times F of tension in the X divided by M. So we know the radius, 0.416902. We know the force of tension in the X, 10 point that. We know the mass, 3 kilograms. So we can calculate that, and we get the velocity is 1.229 meters per second. All right, so we answered the first question. The second question is the period. So looking here, I have the period. So I'll probably use this equation, and we'll just rearrange it for the period. So the velocity is equal to 2 pi r over t. If I multiply by t and then divide by v, I get the period is equal to 2 pi r divided by the velocity. I know radius, I know velocity, that's pi, that's 2, so I can calculate. Plugging in all the numbers, again, the radius is over here, the velocity we just calculated. We get that the period is going to be 2.13 seconds. And that's it. So this is conical pendulum. This works for just an example of when we're dealing with an angle. So we're going to have to use some trig to figure some stuff out. But it all comes back to dynamics of circular motion. So the sum of the forces in the x direction is equal to mass times the centripetal acceleration. And then we just work from there. Your approach to these problems is going to be based on what they give you, what you have, and what you need. But some of the forces, Newton's second law, same verse, different words, and that's it.